I think it first helps to define what an implicit function actually is. So an explicit function, first of all, is one of the form y equals f of x. So it's of the form y equals, so it's explicitly defined. We're extremely explicit in saying what y equals. An implicit function is one that cannot be written in this form. So we're sort of implying what the value of y is. That's where the word implicit comes from. So we're not explicitly saying what y equals. We're just giving a function that has a mixture of x and y's, and it's left for us to deduce what y equals. So an example of this would be, let's say, e to the y plus sine x plus ln of x equals cos of y. And there's absolutely no way that we're going to be able to use algebra to make this say y equals and have all the y's gathered up in one place. We could inverse cos something to get y equals there, but there's still that y hidden in that e to the y. There's absolutely no way that we can rearrange this using algebra to say y equals. So the problem then comes, how do you find what the gradient of that function is? How do you differentiate it? Because if it doesn't say y equals, then we can't make it say dy by dx equals. So, a fact that we're going to convince ourselves of, that differentiating with respect to x is the equivalent, it's identical, to differentiating with respect to y, then timesing by dy by dx. So have a stare at that and pretend, even though it's not, pretend dy by dx is a fraction. Look at what this fraction simplifies to. And hopefully that'll convince you that differentiating with respect to x is the same as differentiating with respect to y, then timesing by dy by dx, because as a consequence of what we've done, these dy's cancel, just leaving d dx. So both sides of this say d dx when simplified. So let's say we've got a function. So we can use the above fact to simplify, sorry, not to simplify, to differentiate functions that are implicitly defined. So let's do an example, e.g., let's say x squared plus y squared equals 45, equation of a circle. So to differentiate this, with respect to x, we dx both sides, i.e. differentiate both sides with respect to x. So let's write that down. So d dx of x squared plus y squared equals d dx of 45. And it would be wrong to say dy by dx equals in this case, because we haven't, the equation doesn't say y equals, so we can't explicitly say dy by dx equals. So we've got to go about differentiating it this roundabout way. So now, that's d dx of x squared plus d dx of y squared equals d dx of 45. So we know how to differentiate x squared with respect to x. That's just 2x. We know how to differentiate the number 45 with respect to x. Any number differentiates to 0. This is the problem here. So looking back up at this fact here, the equivalent of differentiating something with respect to x, we can differentiate with respect to y, then times by dy by dx. So actually, this one here is the equivalent of differentiating with respect to y, then timesing by dy by dx. And that's how implicit differentiation works. We can deal with differentiating something with respect to x that isn't an x by following that rule. So next, we replace any d dx's of functions of y with d dy, differentiate that, times dy by dx, which is what we've done there. So now let's carry on with this differentiation. So this implies that, so differentiate that with respect to x, we get 2x plus, now performing this trick here, we differentiate with respect to y, which gives us 2y, then multiply by dy by dx, like that, equals 0. And there we've done it. We've differentiated a function of both x and y with respect to x. So the next step, we rearrange possibly after factoring out dy by dx to say dy by dx equals. So now we've got 2y dy by dx equals minus 2x, which means that dy by dx equals minus 2x over 2y equals minus x over y. And there we have it, the equation for the gradient of a circle. That particular circle there. So now, when you're finding the equation of a tangent to a circle, I'd recommend using the method that you did in year 1 of finding just the gradient of the radius, then the perpendicular gradient, but this is an option to do it this way. So let's do another. I'll leave you to do one. Let's find dy by dx for this function that's about to appear on the screen. So if you can find dy by dx for that, I'll take over in just a moment. There it is there. So the question is to find dy by dx. So the way I'd lay this out, I'd first of all acknowledge that I was d dx in both sides, but I wouldn't explicitly write it. So I would write d dx both sides to get. So I can see that I've got a function of y here, which would differentiate to 4y cubed, and I knew because I've differentiated a y, I have to multiply by dy by dx. And from this moment forward, that's the way I would think about it. As soon as you hit a y, differentiate with respect to y, then times by dy by dx, and that's the equivalent of the fact that I gave you there. Whenever we have to differentiate a function of y, differentiate with respect to y, times by dy by dx. So 4y dy by dx equals, then differentiate all those with respect to x, 2x minus 6. Which means that dy by dx equals 2x over, 2x minus 6 rather, over 4y cubed. And I can see that'll simplify if I time both top and bottom by a half. X minus 3 over 2y cubed is dy by dx. And notice that to be able to make use of this, we need to know both an x and y coordinate. It's not enough just to know x coordinate. We need to know an x and y coordinate to find the gradient of these functions. So what we need to do now, it's going to be quite often, we're going to have differentials that involve the product rule. But before I go on to that, just a quick note actually. If a function did say y equals x squared plus 6x plus 2, if it was defined explicitly, now all of this time you have been doing implicit differentiation without realizing it, because if we differentiate this with respect to x, we get 1, but because it was a function of y, we multiply by dy by dx equals 2x plus 6. So you've been doing it all along unknowingly, but the reason you wrote dy by dx equals is because of that there. So now we're using the product rule. We'll do another example, e.g. find dy by dx. Just rule that off, so like that. And it's about to appear now. So find dy by dx for that. So if you're making notes on this, I'll give you a moment to get that example copied down. And the first thing that I'm going to do, and this goes for any question I do ever, you should always scan the question because it's probably going to involve the product rule somewhere. So scan through question. Looking for use of product rule. I can see I've got a product rule to do there, and we should do these product rules first. So, just so we don't break the flow of what we're trying to do. So I would always do this as a bit of a sideshow. I'd always put a little star on the question, like that, and do the product rule at the side. So u equals 2x, which means that du by dx equals 2, and v equals y, which means that dv by dx equals 1 dy by dx. And notice I'm keeping the negative sign out of this for now. I'm just going to take whatever my answer is. So the differential is v u dash plus u v dash, which was dy by dx. So there's my differential. And as I say, I keep that to the side so as to not break the flow of what I'm trying to do. So now, d dx, both sides. And let's go for it. So I've got 8x. Take all of this that I've just found. 2y plus 2x dy by dx. Plus, now 3y squared. It's a y, so we're going to have to times by dy by dx afterwards. Plus 6y dy by dx equals, and the differential of 8 is 0. Common mistake is to write equals 8 on after it's been differentiated, but remember, numbers differentiate to 0. Okay, so we've got 8x, take away 2y, take away 2x dy by dx, plus 6y dy by dx equals 0. And notice that the dy by dx is in 2 places here. So now, notice on my step-by-step instructions before, rearrange possibly after factoring out dy by dx. Dy by dx is going to need to be factored out here. So factor out dy by dx. So what that's going to do, if I first take everything over to the other side, so I've got minus 2x dy by dx plus 6y dy by dx. Just move that so I've got enough room. Plus 6y dy by dx equals, and then we've got 2y minus 8x on the other side now. So let's factor out dy by dx. So that implies that dy by dx, and that's 6y take 2x, equals 2y take 8x, leaving us with, if we divide by 6y minus 2x, leaving us with dy by dx equals 2y minus 8x, all divided by 6y minus 2x. Got a factor of 2 in common on both top and bottom, so we times by 1/2 over 1/2. We get y minus 4x over 3y take away 1x. And there's the differential, there's dy by dx. So let's do another example, this time involving the equations of tangents. So remember, we need both x and y values to make this work. So, example here, we'll just look at part A. No, actually, take it back, let's look at part B instead. So I'll get rid of, have a look at part B. I'll just get rid of part A here. So find an equation for the tangent to each curve on the given point on the curve. So we're given the point 3, 5. We're given both an x and y coordinate. Have a go. Take a moment. So remember to scan it for product rules first. So I notice there's a product rule here. So asterisk. And this is where I'm going to do the working. So u equals x, which means that du by dx equals 1. V equals y, which means that dv by dx equals 1 dy by dx. So ddxing both sides now. ddx both sides. So we get 4x minus, I forgot to do that bit there, so v times u dash, v times du by dx, y plus u times dv by dx plus x dy by dx was the differential. So 4x, take away all of that, plus the differential of y squared, which is 2y, and because we're differentiating a y, multiplied by dy by dx, equals not 28. When we differentiate 28, we get 0. So that implies that 4x, take y, take x dy by dx, plus 2y dy by dx equals 0. Everything over at the other side now. Now, technically speaking, we could just sub the point in now and rearrange it to say dy by dx equals, but it's nicer to make the expression say dy by dx equals first. So, 2y dy by dx, take x dy by dx equals, and taking that over at the other side, I get y minus 4x equals 0. Ignore that equals 0 part. No idea why I said that. No idea what come over me there. I've taken it over the other side. It's certainly not equal to 0. dy by dx, 2y take x equals y minus 4x, which implies that, try to get the question on screen actually, dy by dx equals y minus 4x over 2y minus x, which at 3, 5 is, well, sub y equals, sub x equals 3, y equals 5 in. 5 take 4 lots of 3 over 2 lots of 5 take 3 equals, so put in your calculator, 5 take 4 lots of 3 over 2 lots of 5 take 3 equals minus 1. So remember, we're trying to find a tangent, so we've got a gradient. Now, minus 1. We've got a point, 3, 5. And unfortunately, the question is going to go off the screen now, but the point is 3, 5. Therefore, y minus y1 equals m x minus x1. Multiplying it out, y minus 5 equals minus x plus 3. Which means that y equals minus x plus 8. And we have it there. So let's do an exam style question. Well, not an exam style question, let's do an exam question. So this is from a 2007 exam paper. Take a moment to have a go at that. So remember to scan it for product rules. Right, so scanning for product rules. Do it at the side here. So I'm just going to quietly get on with this. You still keep going with yours and check your answer against mine. And hopefully a trap that none of you fell into. It says find the equation of the normal. So the gradient of the normal is the negative reciprocal of that. Very common trap to fall into. Equals 30 over 13. So y minus y1. So the point is 2, 3. So y minus y1 equals m. X minus x1. And at this point, times everything by 13. So that we don't have to deal with fractions. 13y minus 39 equals 30 lots of x minus 2. Multiplying that out. So 13y minus 39 equals 30x minus 60. And get it in the form required, which means that 30x minus 13y, then minus 60 plus 39 is minus 21 equals 0, and now it's in the required form. 30x, take away 13y, take away 21 equals 0. So another variation of question could be to do with stationary points. So let's have a go at that one. Let's do a question on stationary points. So this isn't straightforward. Have a go at it. Get the differential and set it equal to 0. I'll give you a few moments to do that, then I'll take over. Okay, I'll quietly get on with it. $18 differentiates to 0. So taking all the stuff over to the other side. Notice that if I times by a half over a half, it gets it simpler. So minus x minus 2y over 2x plus 2y. So I did that because I could. There's no pressure to. You probably wouldn't lose a mark in an exam unless it said fully simplify. So there's dy by dx. Now at a stationary point, dy by dx, as you know, equals 0. So minus x minus 2y over 2x plus 2y equals 0. Or more specifically, the only way that fraction is going to equal 0 is if the numerator of the fraction equals 0. So the denominator is pretty irrelevant here. Basically, we know the stationary point happens at the solutions of x minus 2y equals 0. So, which implies that x equals 2y. Now, normally what we're given at this point, when differentiating explicitly, is a number, an x-coordinate of the differential of the stationary point. But we're not here. We're given an equation. So you'll hear me typing away here. What I'm about to do is put this in Desmos and show you exactly what's happening here. So I'm just typing the function into Desmos now, and you'll see it on the screen in just a second. So 4xy plus 2y squared plus 18 equals 0. So there you have it there. There's the curve, and we can see that stationary points are there and there. So we also got the solution x equals 2y. So x equals 2y. Sorry, x equals minus 2y it was. And we can see that indeed this line, x equals minus 2y, does pass through the stationary points. And I've also given away what the answer is there to both of them. We've got minus 6, 3, and we've got 6 minus 3. They're the answers we're working towards. So x equals minus 2y. And we can see that if we solve our solution to that differential equaling 0, i.e. x equals minus 2y, if we solve that simultaneously with the original equation, we'll find the two stationary points. So, again, what we don't get is a solution to the equations. We don't get that. We don't get x equals the x squared at the stationary point. We get a second simultaneous equation to solve with the original curve to find where the stationary points are. And that's the difference with the method on implicit differentiation. So let me just correct that. X equals minus 2y. There it is there. So let's do that now. Let's solve x equals minus 2y simultaneously with the original equation. So we know x equals minus 2y, which means that, so we've got minus 2y squared, that's x squared, plus 4 lots of x, which is minus 2y, times y, plus 2y squared, plus 18 equals 0. And remember, we're working towards the answer, as we saw on Desmos, we're working towards the answer minus 6, 3 and 6 minus 3. So take that quadratic equation, continue to solve it. So y is plus or minus 3. And we need the corresponding x coordinates for that. But we've got a great way of doing that. That's much easier than subbing in back into the original equation. We know that the stationary points lie on x equals minus 2y. So x equals 3 implies y equals minus 2y, which is minus 6. X equals minus 3 implies that y equals 6. So we've got the 2 points. 3 minus 6 and minus 3, 6 are our answers. So nice and straightforward. Let's try another. One last example. And the algebra in this question is a little bit more difficult. So have a go at that question there. I'll take over in just a moment. So I think the first thing to do here, rather than using the chain rule to differentiate that bracket squared, I would multiply out the brackets first of all. So again, a bit of a sideshow. So I'd rewrite the equation as x squared plus 2xy plus y squared equals xy squared. And notice here I've got two product rules to do. So I'll do that one first, and that one a double asterisk. The second asterisk So we've got two differentials there. So that's now d dx both sides. So 2x plus the differential we worked out with a single asterisk. 2y plus 2x dy by dx plus then differentiate y squared becomes 2y dy by dx equals the differential of that, which is y squared plus 2xy dy by dx. And make sure all the dy by dx's are on one side and all the non-dy by dx's are on the other side. And if you want, we can do that and factorize in the same line. So if I move all the dy by dx's to the left-hand side, I've got 2x plus 2y. That's those two there. Then I'm going to take this one here, take 2xy equals all the non-dy by dx's. So on the right-hand side, I've currently got y squared. And I'm going to take these two over to the other side to get minus 2x minus 2y. Which means that dy by dx equals y squared minus 2x minus 2y all divided by 2x plus 2y minus 2xy. And even more difficult, it's said at the point where x equals 1 we don't have a y coordinate. However, we can get one by subbing x equals 1 into that and finding what y equals. So a lot of work for 7 marks here. Try that, get the y coordinate, and then find the gradient. Okay, so summing it in there. So let x equals 1, which implies that 1 plus y squared equals 1y squared. Let's get the y coordinate, which implies then 1 plus 2y plus y squared equals y squared. Take y squared from both sides, which implies that 2y equals minus 1, which means that y equals minus 1/2. So now we've got a y coordinate, now we can find the gradient. So let xy equal 1 minus 1/2, which implies that dy by dx equals, so minus 1/2 squared minus 2 lots of 1 minus 2 lots of minus 1/2, all divided by 2 lots of 1 plus 2 lots of minus 1/2 minus 2 lots of 1 times minus 1/2, which is equal to, let's put that in the calculator, to save time I'll put it in as 0.5 minus 0.5 squared minus 2 lots of 1 minus 2 lots of minus 0.5 over 2 lots of 1 plus 2 lots of minus 1/2 and notice these calculations I should be able to do in my head, but I'm taking no chances, nor should you in an exam. Do everything on the calculator, because those exam nerves might get to you. Equals minus 3/8. And that's the answer. So hopefully you got that. So that's really, that's it. That's implicit differentiation for you. So that's where we'll leave it. So have a go at the worksheet that I've put in the archive area. Got loads of questions on it, and have a go at the exam questions on the website. So have a good rest of the weekend. There's going to be no lesson for the next... so there'll be no lessons until the Saturday before we go back over Christmas now. So no lessons for those for the next 2 Saturdays, and the third Saturday we'll have one. So have a good rest of the weekend.